It would be wonderful if we could solve every differential equation we encounter. But the fact is we can't. I mean, there are really big challenges. Even just simple integration, there are some things that we just don't know how to integrate. So if we can't even do simple integrations, we can't solve every differential equation. But there are cases where we say, look, even if we can't solve the differential equation, we can understand the long-term behavior, the qualitative behavior, what's happening to this differential equation. That's our goal for today. But first, we're going to finish up talking a little bit about an example involving some population models. Let's begin. So you might recall that at the very end of our discussion last time, we were talking about the logistic model. And so when you talk about the logistic model, it's where you have the derivative is some constant k, p, m minus p. So this is, again, the logistic. And in the past, we were able to derive, hey, what's the solution? What does it look like? And, well, it's not trivial, but it turns out it's some m times p0, well, that's the m, p0, initial population, divided by p0 plus m minus p0, e to the minus kmt. Now, sort of the intuition about what's going on with this, and I think it's good to talk about the intuition, is suppose we were to graph what's happening. Now, we can see that there's two very, very easy solutions in the sense that they're trivial. And that is, you say, okay, take your differential equation and set it equal to 0. And ask, are there any solutions? And the answer in this case is yes, there are two. Namely, if you set p itself equal to 0, well, that makes this side equal to 0. But notice that the derivative of any constant is automatically 0, which means that one of the curves that solves the logistic is, of course, here. And similar, if you set p equal m, you get 0 over there, and that's what we have. Now, we're going to assume that k is positive, since that's what the usual model involves. And in between 0 and m, things go uphill, and so our curve will drift up. So if we start below 0, if we start just above 0, this is what will be happening. If we start above m, our curve will drift down, and it'll head towards him. If you start below 0, it will move downhill. So there we go. There's our basic model and what it looks like. Now, let's do an example that uses the logistic model. Suppose that the population of a country, which we measure in millions, follows p prime is equal to some constant p times 200 minus p, where k is a constant. All right, so we can see automatically that we have our nice differential equation. Aha, this is the logistic model. But we also see something else. We say, look, we can see what m is. It's 200. So in our case, we say, okay, m is 200. Now you might remember what is 200 or what is m. That's measuring the carrying capacities, sort of saying, what does the environment support? What is it able to sustain? And that says it's able to support a population of 200 million. And so if our population is above 200 million, we will drift down. If the population is below 200 million, we'll drift up. So we always move towards 200 million. All right, now there's some additional information. Its population in 1960 was 100 million. All right, so that means we are somewhere between 0 and 200. We're halfway in between. So we're going to be going up towards 200. And there's more. Was then growing at a rate of 1 million per year. Predict the country's population for the year 2020. All right, there we go. Now, let's untangle this. What information do we have? Now, we certainly have some initial information, which is the 100 million. Now, the question is, what do we think of as our initial time? Do we think of it as 1960, or do we think of it as saying reset to 0? And the answer is we can pick. Because notice, time does not show up in this model, which means you can pick a convenient time for us. So we're going to say, okay, we're going to let 1960, that'll correspond to time equals 0. And then then we have that our population at that time equals 100. Okay, good. Now we have a lot of pieces. We have our M, we have our P0. We still miss one thing. We don't have K yet, but that's all right. The problem continues. It was growing at the rate of 1 million per year. All right, so what do we have? Well, we see that there's a number here. And what is this? Well, we see the word rate. That means it's a derivative. So the derivative at time 0 is 1 million per year, which means it's 1. Now, one other key word here we should pay attention to is the word growing. That tells us that our derivative is positive. Now, you might say, do we need to pay attention? Well, yeah, it could be say, hey, the population is declining at a rate of 1 million per year. And that would indicate we needed a minus sign. So pay attention. Sometimes there is some sign terminology involved, and we don't want to miss anything. We want to get all our points, right? That's our goal. It's always our goal. We want to understand everything. Okay, so translation, we have that P prime of 0 equals, whoops, why do I put prime? Prime goes upstairs. P prime of 0 equals 1. This is where I'm measuring things in terms of millions. Now, what is P prime of 0? Well, it's what's our population at time 0, right? It's 100. So we're plugging 0 into this side. So it's K times our population at 0 times our 200 minus our population at 0, which means it's K times 100 times 100. So that information lets us solve for K. Now 100 times 100 is 10,000. So that tells us that, K is 1 over 10,000. And now we have all our pieces. And because we have our formula right there, very handy, nice, we can solve. So we get the following. We have our population at any given time is equal to, and now we start putting our pieces in, so 200 times 100 divide by 100 plus 200 minus 100, e to the minus, and there's a 1 over 10,000, and that's the K, times M, which is 200 times T. And there we go. There we go. Okay, well, we can clean that up. So notice a couple of things. That's 100, that's 100, there's 100. So we can take all the hundreds and we can cancel them out. So we say, nice. So that gets rid of those. And so what do we really have? Well, we have this is equal to 200 upstairs, downstairs 1, that's what is left over after you cancel the 100, and then plus E. Now here we can do a little bit. We can cancel some zeros, right, because there's 200 and 10,000, so it's like dividing by a 10, and so it's like 2 over 100. Well, that's 1 over 50. So we get E to the minus T over 50. There we go. Now, that's our population any time. What do we want? Well, we want our population in the year 2020. Okay, well, so what do? Do we plug in 2020? No, no, be careful, because remember, we reset. So 1960 corresponded to time equals 0, so this says 2020 would be at time 60. So we'll plug 60 in, and let's see what we get. We come up with our answer that our population in 60 years later, just 2020, is 200 divided by 1 plus E, and then we have 60 over 50, which is minus 6 over 5. And there we go. There we go. Great. Now, if you plug this into a calculator, I believe it's about 153.7, which of course, remember, means million people. And all right, That's the answer. Now, we're done, but it's okay for us to take a second and ask the question, is this reasonable? And because sometimes people just say, okay, I have a number, I move on, I won't think about it, even though their number might not make any sense. Suppose that we had done this computation and out came the number 15, like 15 million people. Would that be reasonable? Well, no, because what's happening? We're starting at 100, and we can see that we should be drifting up to 200. So our answer should definitely be somewhere between 100 and 200. So if we somehow got 15, that's too low. Same idea, if we got like 320, that's too high. So we know our answer should be somewhere between 100 and 200. So that's a promising sign. We also think, okay, look, it's growing at 1 million per year. There's 60 years. So, 60 million is a really bad estimate, but, it's not so bad. But should we expect we should have more than 60 million or less than 60 million? Well, if we look at the model, it seems that our rate should be slowing down. So it says, look, we should have gone up by a bit less than 6 million, but not terribly less. That seems to agree. So it's a reasonable answer. Probably a sign we did something right. Yes! It's wonderful to do things right. Good. All right. Well, now we're ready to sort of switch gears. But before we do, I think it's useful to actually look at the logistic model as an example of what's coming up. So you'll notice that we have these two sort of very simple cases, simple solutions, namely at 200 and at 0. And they also are very different when you think about what's happening near those points. So for instance, suppose we look at 200. Notice that if we are around 200, so if I start a little bit above 200, or if I start a little bit below 200, what happens? Well, I move towards 200. So somehow 200 is attracting its nearby neighbors. It says, hey, if you start near me, you're going to come towards me. On the other hand, we have 0, and that's also the same idea. It's a constant solution. But again, take a look at the neighbors of 0. And what do we see? It says, hey, if you start near 0, just above it, you move away. And if you start just below it, you also move away. So somehow 0 is repelling. It's moving things away. And so we're like, oh, okay, so there's this sort of two behaviors. We attract what's nearby, or we repel what's nearby. And can we be more specific, and should we give some names to this? So that's where we're going. So we're going to talk about what we call an autonomous differential equation. And so when you think of the word autonomous, well, auto really is talking about the self. So it says, hey, I just want to describe by myself what's going on. And so in this case, what does it mean? Well, it's a differential equation which can be written in the form y prime equals f of y. Now, what's missing in this differential equation? There's no other variable. There's no f of y comma x or y comma t. It's just y. And so I say, oh, so really, if I want to know the behavior, I don't have to know what time I'm at. I just have to know what's my current value, what's my current output. That completely determines whether I'm going to go up or down. So, great. Okay. So, what can we say? Well, it turns out that in this scenario, we can actually say things about the solutions even if we can't find them explicitly. What we can do is we can say, well, we understand the behavior. Basically, we can say, hey, do I go up or do I go down? And we can use that to say what happens in the long term. So, what do? Well, we are going to talk about our critical points. Now, what are these? These are where f of y equals 0. Okay, well, what's special about f of y equals 0? Well, if I have a critical point, so in other words, suppose I have f of, say, k equals 0, then what does that mean? Well, that says y equals k is a solution of the differential equation. Why? Because the derivative of a constant is 0. F of k is 0. 0 equals 0. So what we get is we say, oh, so these critical points are where we have zeros. All right, great. So we're finding constant solutions. Now, what happens in between the constant solutions? That's the second part. So we're going to look at what's called a phase diagram. And the goal of a phase diagram is to say what's happening qualitatively. So you might say, what does that mean? Well, quantitatively, we might say, we can say exactly what the solution is. You give us a number, we give you a value. We aren't going to be able to get to that level. But what we are going to say is, what's the behavior? How is it behaving? Is it going uphill, going downhill? In other words, am I increasing or am I decreasing? And so how do we figure that out? Well, what we do is we say, okay, we know where the critical points are, and then we say, what's the sign? We saw the sign, and it opened up our minds. We saw the sign. Because the sign tells us, are we increasing or decreasing? Okay, so what's the idea? Well, what we can do is we can start with plotting. Suppose I have y prime equals f of y. So what I'm going to do is I'm going to sketch. So here I'll have y, and here will be y prime. So in other words, I'm going to think of this as a function. And we'll plot, and let's see, what do we have? Well, maybe we'll have something that does that. That's a perfectly valid thing. That's a potential differential equation. All right, and now what are we after? Well, what we're after is saying, let's understand the behavior. So the phase diagram says, all right, we're just going to think of it as an axis. And we say, all right, we'll find the zeros of the function. Now the zeros, that is where we hit the axis in this picture. So here are our critical points. All right. And there we go. Now, what happens? Well, from here, we say, okay, look at the value of the derivative. Between the critical points, the derivative will always have the same sign. And so we start by saying, okay, are we positive or negative? So we come up here and say, well, we're negative when we're below the axis. So here we'll have y prime is negative, and over here we'll have y prime is negative. On the other hand, we'll see, oh, y prime is positive, and y prime is positive. And now we say, okay, what's going on? Well, what's going on is wherever y prime is negative, that says, oh, we're going to be moving to the left. Where y prime is positive, move to the right. Because, y prime negative says we're decreasing. Decreasing is a left motion. And so we have that. Where y prime is positive, we are moving to the right. That's a right motion. Okay. Now, what's happening? Well, we say a critical point is stable if solutions nearby converge towards. So we're stable if you're nearby, you move towards the point. So to move towards the point, we want to have the arrows pointing in. So an example of a point which is stable, well, we have one. This point here. This is a stable point. All right. Now, what else? Well, we have a critical point is unstable if solutions move away. So in other words, if I'm not exactly at that critical point, if I'm just next to it, then I start to drift away. And that's true on either side. So this point is unstable. Both the arrows point out, away from it. And now there's a third possibility which happens, which says a critical point is semi-stable if we say, look, on one side we're moving in, but on the other side we're moving out. So in other words, the arrows point in the same directions on both sides. So this is an example of something which is semi-stable. So semi-stable. So there we go. And that's the idea. So what we have is the phase diagram. Just to be clear, if you're asking what is the phase diagram, this is the phase diagram. And by understanding the direction of the arrows, we can read off stable, unstable, semi-stable. Now, your eye might have been drawn to something, and you might be saying, wait, Steve, hold on a second, I think you missed something. All right, let's talk about what I might have missed. What about these points? Aren't they important? You know, places where you have somehow f of y is max or mins or something? And the answer is no, they're not. We care about where we cross the axis. So these are red herrings in some sense, making you think they're important, but in terms of saying, am I moving up or am I moving down, they actually don't matter. Now, you might say, what can we do with this? And what we can do is we can actually translate this into a rough picture of what the solutions will look like. All right, well, how do we do that? Well, we graph. And we're going to produce a new graph, and this is going to be a graph roughly of what the solutions to the differential equation look like. Now, we're going to label our axes here just so we understand. It's a different picture here. So I'm going to have x, and I'm going to have y. Now, what happens is we have to translate these points. So let's suppose we knew where these points were. All right, so let's say this was at -2, this was at -1, and this were at +2. Okay, well, I didn't plan very well my axis here, but all right. So here we go. So we have -2, -1, and +2. And these curves are solutions to this differential equation because they're constant solutions. We found them. And now what we say is, all right, what's happening in each one of these? Now, the phase diagram, if we could take it here, we could actually translate it just doop. And so it's telling us about behavior. So for instance, it says we're going down, then we go up, up, and then we come down. And now we say, all right, we understand the behavior in between each little constant solution, and so we can draw. So for instance, the fact that this says goes down, that just means we move down. In between, when we're moving up, that says we move from the bottom to the top. So we're going to come up in some way, shape, or form. Now this is a rough approximation. Here, all right, we are moving up again. So we're going to move up again. So we come off the curve and head towards. But it should be emphasized, we never actually hit this curve. We only approach it. And similarly, when we say we come off, we come from near the curve and approach. The curves never intersect. The solutions never intersect. All right. And then finally, we're coming down. So we come and we approach this curve. And there we go. There's our solutions. And that's a rough idea. Now, you might say, is that really that simple? And basically, yes. Because in between, we can only go up. That's what this information is telling us. We can only go uphill. So there's not going to be something where it's like, oh, it goes up and then wiggles and then approaches. No. There's no wiggling involved. Now, we might have the case where we go up, we steepen a little bit, shallow a little bit, steepen a little bit, and then flatten. Well, that's being captured by this type of thing, but that's more subtle. And for us, we're satisfied just with the idea that says, we see the basic behavior. We go up or we go down. And so we can even start to answer questions. So for instance, suppose we say, at some time, we start at 0. Now, I don't care what time it is, because when I'm dealing with an autonomous differential equation, time really doesn't matter. The output matters. So suppose that at some point I'm at time 0. What has to happen? Well, the answer is I'm going to have to go up and move towards 2. Why? Well, because if I'm at time 0, if somewhere I'm at, my output is 0, so let's say at time -5, I'm equal to 0. Well, then I have to follow my arrow, and my arrow says move to the right, and we're going to move up to the next critical point. So we can say what happens. So in particular, we're going to say, look, you're either at -2, or if you're below -2, you go towards infinity. If you're between -2 if you're above -2 but less than or equal to -1, in the long term you move to -1. Otherwise, if you're above -1, in the long term you move to 2. So we can say, hey, we only have really 3 possible outcomes, right? Well, technically there's a 4th outcome. So our possible outcomes are you move towards 2, and that's for anything that's above -1. You move towards -1. That's for anything that's above -2, less than or equal to -1. You stay at -2. That was the outcome that I didn't specify before. And that's if you start at -2. It's so delicate, -2, that the only way we could end up at -2 is to begin there. And the last outcome is we head towards -infinity. And that's if we start anywhere below -2. So there we go. We can understand the long-term behavior. Okay. That was quite a lot. Let's try it. Practice, right? See what we can get. So, here we go. For the differential equation, y prime equals y squared times y minus 2 times e to the y minus 2, find all of the critical points and classify each critical point, stable, unstable, semi-stable, draw the phase diagram, and do a rough sketch of some typical curves. So, essentially, we're going to do what we just did, but with a specific function in mind. So we can say, okay, let's see what's going on. Now, you might say, I don't know how to sketch this function, y squared times y minus 2 times e to the y minus 2. Well, we don't really need to sketch it. But what we do want to do is say, okay, what does this look like in terms of where the zeros are at? So we'll start by finding the critical points. So the nice thing is, they already factored it for us because they care about us. They want us to be able to answer this question. Now, when you have a bunch of stuff multiplying together to equal 0, the only way that can happen is if something equals 0. Okay, so we say, well, what could equal 0? Well, if y squared equals 0, that would be at 0. If y minus 2 equals 0, that would be at 2. And if e to the y minus 2 equals 0, well, that would be at, when e to the y equals 2, take natural logs, you'd have natural log of 2. Now, 0 and 2 are pretty clear, we know that. Log 2 is a little bit more delicate. Now, where is log 2? So in other words, is log 2 below 0, between 0 and 2, or above 2? And if you don't automatically say, that's okay. We can just think about it a little bit. If you had a calculator, we would know it pretty quickly. We can actually do a couple of things. And we say, well, look, there's 2 values for log we know. So we know log of 1 is equal to 0. And we know log of e is equal to 1. Now, e is 2.71828. So 1 to e, 2 is in the middle. And log is an uphill function. So that says that log of 2 is somewhere between 0 and 1. And, all right, that's true. So we say, okay, great. We know now, hey, we have where our critical points are, so we can start drawing the phase diagram. So here is our y, and we mark our points. 0, log 2, and 2. And now, what do we need to do? Well, we need to think about the sign of the derivative in each one of these 4 pieces. So we say, okay, pick a number. any number in between. And, all right, so suppose I pick something bigger than 2, like 1,000,000, or 3. Yeah, they both work. So we just go through and say each part. Well, that's positive. 3 minus 2 is positive. E cubed minus 2 is positive. So everything's positive. So that says y prime is positive, which tells us that we are moving up. All right, between log 2 and 2. Well, we said, log 2 is below 1, so I can pick 1, because that's below 2. 1 squared, positive. 1 minus 2, negative. E minus 2, positive. So positive, negative, positive says, this is negative. So we're going to be moving down. Okay, between 0 and log 2. Now here you're like, oh, what do I know? Well, look, think about 0.00001, right? Just to the right of 0. And then you're fine. And then for all practical purposes, essentially 0, right? But okay, a little bit bigger than 0 squared, positive. A little bit bigger than 0 subtract 2, negative. And then e to the basically 0 is basically 1. Subtract 2 is negative. So positive, negative, negative. And if we say, that means we're positive. We're moving to the right. All right. And then below 0. Okay, minus 1,000,000. Square, positive. 1,000,000 minus 2. Negative 1,000,000 minus 2, still negative. And e to like the minus 1,000,000 is 0. Subtract 2, negative. So positive, negative, negative means we're still positive. And there we go. And that's it. Yeah, it's pretty simple. It's like the mathematician Beyonce might say, to the right, when the derivative is positive, we move to the right. Exactly. And then, of course, there's the other part, to the left, when the derivative is negative, we move to the left. Yeah, it's all about orientation. Okay, good. So now we have our phase diagram drawn, and we say we understand what's going on here. But, of course, we need to classify. And here, it's going to be pretty quick. We can classify once we have our arrows, say, look, we're going up. That means that 0 is going to be semi-stable. Because, it just depends. The behavior on the two sides is essentially different. One heads towards 0, one moves away from 0. For log 2, from both sides we're approaching, that says log 2 stable. And then for 2, we move away, so that means unstable. Now, by the way, another thing that we could have done, if we were careful and comfortable with it, is to say, well, look, we know where the zeros are, and the question is, should we cross through, or should we sort of bounce off? Now, this comes back to understanding, well, how do we know if we pass through versus how do we know if we bounce off? It says, well, how often are you a root? See, 0 is a root twice. So if you're a root twice, you're not going to change the sign. On the other hand, 2 and log 2 are singular roots, so we're going to pass through, which means we should change sign at 2 and log 2 and not change sign at 0. And if you know that, then you say, look, if I just know the sign in one place, and I know how my signs change, I can determine everything. But that's if you're comfortable. If not, just test. And recall, you don't have to stress very much about, which point do I pick? The answer is pick any point in the interval. So like I said, you could have picked 3, you could have picked 1,000,000, could have picked 1,000,000,000, could have picked 4, could have picked pi, anything bigger than 2. The thing you can't pick is you can't pick 2. We need something above 2. So it's not so bad. If anything, this might start to say, hey, this was like the first derivative test we learned about back in Calc 1, right? Yeah, spiritually, yes. That is essentially the same ideas coming into play. Okay, so we're not quite done yet. We have to do a rough sketch of some typical curves. Now, what does that mean? Well, we're going to plot here. So here we have our x-axis. Here we have our y-axis. Now, we're just assuming the variable that we didn't have listed as x. It might be t. Well, that doesn't matter. It's just our other variable. And we say, all right, sketch our constant solutions, which come from the critical points. So we have 3 of them. So we have 0, and we have log 2, and then we have 2. So those are actually 3 sketches, and there's nothing rough about them. Those are highly exact, precision sketches. Now for the rest, we think of like saying, okay, look, this is something telling us about what's happening in the y direction. So we see, for instance, that we're going to be moving up, up, down, up. So I'm just taking this information and translating it here. And once we have that, then drawing the rest of the sketch is pretty quick, right? Because it says, look, if I'm below 0, I move up towards 0. So, all right, so I move up towards 0. If I'm between 0 and log 2, I'm going to move up. And so there we go. If I'm between 2 and log 2, I move down. So move down. And if I'm above 2, move up. And there we go. There's our sketch. That's it. That's a rough sketch. Now, is it precise? No, but it captures the behavior. And we see what happens. So, for example, we say, oh, if you pick a number like 3, you're just going to always keep going up. You'll head off to infinity. Pick a number like -10, you're going to head towards 0. If you pick 1, we'll move down to log 2, and so forth, and so on. And so we have our wonderful behavior of our differential equation. Now, one other thing to point out is our sketches will be invariant if you move left and right. And why is that? Well, the answer is because autonomous says, look, you only care about the y. So it doesn't matter where you start in terms of x. It's going to be the same curve, just shifted over. Because y prime equals fy doesn't depend on x. And that's why it will be invariant under our shifts. All right. Well, let's do one more problem. And one more important idea. So here we go. What can we say about the behavior of the critical points for y prime equals hy minus y cubed for various values of the parameter h? Now, this is going to be a very interesting idea here because we don't have one differential equation. We actually have a family of differential equations. So as you change h, you're getting different differential equations to come out. And so we're saying, okay, well, what happens for our different differential equations? What can we say about our critical points? How are they behaving? So, well, let's think about it. So we have to think about what's going on. We start by saying, well, let's find the critical points. That's not too hard. So we say, all right, we're going to take hy minus y cubed, and we'll set it equal to 0. Well, that's the same as y times h minus y squared equals 0. And we end up with a couple possibilities, right? We get y equals 0, or we get y squared equals h. Now, here, let's be careful. We don't want to say, oh, square root of h. And then you might hear me say like, and you're like, oh, plus or minus square root of h. And I'm like, we have to be slightly careful here. We're thinking about real value when we set this up. So what we should think about here is we say, look, that says y equals plus or minus square root of h. This assumes that h is greater than or equal to 0. But otherwise, if there's nothing, if h is below 0. So this little symbol here, that's the symbol for empty, nothing. It comes from the Norwegian alphabet. Roughly, it sounds like So, if someone asks you, well, what's the solution? And they're like, yes, exactly. There's nothing. It's empty. Aha. Yes, of course. That's what I meant. Okay, so we have where our critical points occur, and we say it depends on h. So what we're going to do is we're going to introduce another diagram. And so we're going to have to keep track of all these wonderful things going on. So I'm going to think of h here as being my axis. So that's my parameter. And y is my other axis. And so what happens? Well, we see that y equals 0. Well, that's always a solution. So we're going to say, all right, we'll plot that. So here's y equals 0. And then we have h equals y squared. Well, that's a parabola turned on its side. All right, so there's our roots. In other words, there's our critical points. So in particular, we say, okay, there's either one critical point or three critical points. All right, well, so how do we figure out the different behavior of these critical points? In other words, stable versus unstable, so forth and so on. And the way we can do it is we're going to look at the behavior for some choices for h. So we'll say, well, let's look at h equals something here. Let's say h equals -1, and we'll see that. We'll look at this point. That seems really an important point, h equals 0. And then we'll look somewhere over here and say h equals +1. Now, you might wonder, why are you picking those values? Well, they're simple. Could we pick other ones? Yes. Do we have to pick a lot more? And the answer is not really. I mean, in essence, what do we want? We really want to say, what's the behavior? And so what we'll see is that these three really capture the different behaviors for choices of h. So let's see what's going on. So when we have h equals -1, well, we can do what we did before, where it says, okay, that says we have y prime equals -y minus y cubed. So that says, well, things are very negative, and we can sketch, as we had before, where we have the y versus the y prime. And this is something that can be sketched, and I'll just tell you what it looks like. You can see that the -y cubed is the dominant. Now, y cubed normally would come up, so -y cubed flips it. So it would actually go down, and then the -y makes it so, as we come through, that we have a slope of -1. So this is the sketch of our differential equation. All right, well, now we say, okay, probably should have chosen a different color, just to emphasize. In terms of the phase diagram, well, there's only one root, which is 0. Now, what can we say about this? Well, we see that below 0, y prime is positive. Above 0, y prime is negative. So positive means we move up. Negative means we move down. So what can we say about 0? Well, what we can say is that 0 is stable. All right, so that's what's happening when we look at h equals -1. Okay, well, how about h equals 0? Well, in that case, it's a very simple differential equation. In fact, this is a differential equation that we could solve without very much effort, but we're not going to just because we're not asked to. We just want to get the hang of what's going on here. And what happens here is what? Well, we have -y cubed, and so we actually come in almost flat, and then we go down. But again, we see, okay, there's one critical point, which is 0, and again, we're positive below 0, which means we go up, or negative after 0, which means we go down, which means 0 is still stable. Great. So in some sense, nothing has changed at 0, which is not too surprising. There's only one critical point. But things are about to change, right? Yeah. So before we do our last case, we can point out that what does a typical solution look like? Well, here we look at xy, And our curves, well, we know y equals 0 is always the solution, and we're moving up. If we're below 0, moving down if we're above 0. And the picture is essentially the same in this case. So we still have 0 as a solution. The only thing is, how we approach 0 might be a little bit different. But still, qualitatively, the same behavior. Now, let's talk about h equals 1. What happens there? All right, so at h equals 1, what do we get? Well, we get that y prime is equal to y minus y cubed. Now, in this case, you might say, well, how do we sketch that? But it's actually not too bad, because we can talk about where the roots are, because we know the roots. We actually have them explicitly worked out, 0 and plus or minus square root of h. Well, in this case, that means plus or minus 1, which means that when we sketch this diagram here in our y prime axis, and I've also marked my axes over here, just because we have 3 different scenarios, right? Y versus y prime, x versus y, h versus y. So we've got to keep in mind what the diagrams represent. So here we say, oh, well, we can see we have our roots, -1, 0, +1. And we can see, look, in the long run, we're going to go down because the minus y cubed dominates. And then on the other direction, we're going to be coming from above. So our picture looks something like that. All right, well, time for our phase diagram. So we have our roots are 0, minus root h, and plus root h. And what do we see? Well, we're going to be moving up because we have positive. Then we're moving down because it's negative value. Moving up, positive. Moving down, negative. And we can go through and mark these. So the minus root h is stable. I'll write that as an S. The 0, well, right, we're moving away on both sides. So unstable. And here, positive root h, back to being stable. So it's very sus, you might say. All right, stable, unstable, stable. So notice something. 0 used to be stable, but then it switches to unstable. So there's this sort of change in behavior. So there's something dynamical going on. And this really is going into the topic of dynamical systems, which is a beautiful topic in math. So what do our solutions start to look like? Well, what we can see now is if we have our x, y, well, we have our 3 solutions. And so we'll have our positive root h, our 0, and our minus root h. And we'll move positive root h, is stable, right? So it attracts solutions. And so we'd have that. And also minus root h is stable. So it attracts solutions as well. So we have that type of behavior. And that's it. That's our diagram. Now, what we can do is we can actually think about what's happening over here. So I can translate, because this is y, so I can take this and do a translation. Just, right? Flip it over. And so what's happening, let me grab a different color here. So we're moving down, up, down, up. And then here, again, we can do our translation. So down, up, down, up. So it's always the case that we're moving up, sort of below this envelope, and then inside the envelope, we are sort of moving away. So finally, we can say, where do we have our points? Well, our stable points are along here. So this is where we have stability, so stable. And then our unstable points would be along here. There's our unstable points. And that's it. We've completely characterized stable versus unstable for our various values of h. And of course, this is just a very simple scenario. You can get much more exotic scenarios. And it's a wonderful topic. But that's it for now. Thank you, and we will continue again in the near future. Bye.